Alright, hi, this is Max Leamy, and for my interesting mathematics project, I decided to do non-Euclidean geometry. So to introduce non-Euclidean geometry, I wanted to talk about the differences between Euclidean geometry and non-Euclidean geometry. So the geometry that we study in class up until pre-calc this year has been called Euclidean geometry. And it's basically geometry that's on a flat plane, and it contains 5 postulates that Euclid created in order to define it. And the geometry that is not based on a flat plane or any other geometry is called non-Euclidean geometry. And there are 2 other main types of non-Euclidean geometry that I studied for this project. I did spherical geometry and hyperbolic geometry. And each branch of geometry has its own postulates and properties that in order to point it out from one another or to identify it. So this is Euclidean geometry, hyperbolic geometry, and spherical geometry. So first, in order to identify the properties for each of the different types of geometry, I had to go through Euclid's postulates. And so for the first one, a straight line segment can be drawn joining any 2 points, which means that I have any 2 points, I can join them together with a line to create a segment. Number 2, any straight line segment can be extended indefinitely in a straight line, which means that any line segment that I have, I can extend in both directions in order to create a straight line. Number 3, given any straight line segment, a circle can be drawn having the segment as a radius and one endpoint as a center. Basically means that any of my straight line segments, I can have one point as the center of the circle and one point as a point on the circle, and that in turn creates the radius of the circle. For number 4, all right angles are congruent, meaning that it doesn't matter if my 2 line segments that are perpendicular, it doesn't matter how long they are, the right angles are always going to be the same. They're always 90 degrees. And then for number 5, if 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect each other on that side if extended far enough. So this is the only postulate that hasn't completely been proven, but it's kind of like universally accepted for Euclidean geometry, and it basically means that if a line is parallel at one point, then it'll be parallel forever. So I started off with spherical geometry, which was first thought of after noticing that on a map that the smallest distance between 2 points on the globe basically is not a straight line, but it's actually like a curved line. And in order to account for this, it means that because the distance of the circumference or the size of the circumference of a sphere is altered as you move further from the center. So like imagine if you move further from the equator, then your circumference of your circle is smaller and smaller and smaller. And then for spherical geometry, there are specific properties that help to make it different than all the other geometries, such as for a spherical triangle, if you add up the sum of the degrees of the triangle, it's more than 180. And I can show you that right here. So basically, because these lines are straight on a sphere, but they occur to kind of like jut out or curve into the angle, it creates this effect where the angles measure larger than the sum. The sum of the angles measures larger than 180 degrees. And then this also proves Euclid's 5th postulate is false, because even though these lines could be parallel at one point, the lines will eventually cross each other at some point on the sphere. So next we have hyperbolic geometry. And this geometry was originally just considered like hypothetical because no models were created at first that could basically create a constant negative curvature, which is the opposite of spherical geometry, which is constant positive curvature. And then eventually models were made, such as this crochet model that was created that has constant negative curvature. And so some special properties of hyperbolic geometry are that it also proves Euclid's postulate is false, because even though, as for instance in this picture, these 2 lines are parallel at one point, they eventually go away from each other and are not parallel anymore. They don't have the same slope. And then for a triangle in a hyperbolic plane, the sum of the degrees of the triangle is less than 180 degrees, because it's like the opposite effect of spherical geometry, where even though these lines are straight on the hyperbolic shape, they appear to curve inwards and create these very acute angles, and it's pretty easy to see them. And that wraps up my presentation on non-Euclidean geometry. Thank you, and I hope you learned something.